undergraduate at Boulder, 2007, working on coherence, electronic coherence in dense atomic vapors. She then went on to do a postdoc at Oxford, where she again worked on atomic solid-state memories. She was briefly an assistant professor at the University of Delaware before joining the University of Illinois in 2015, where she does quantum optics, atomic molecular spectroscopy, and more recently, she'll tell us about this work in collaboration with Paul Kwiat, quantum networks. Please welcome Gina.
Yeah, thank you, Benjamin. Yeah, so it's a pleasure to be with you today. As you see on the screen, I'm going to talk about the Public Quantum Network. Did any of you see the Public Quantum Network launch event? Okay. All right, so for many of you, it might be new. Let me just give a brief introduction. So this is a outdated photo of my group. Many of the people have changed over to new graduate students. What we study is quantum networks, which I'll talk about today. We also do a lot of work on building sources for things like quantum networks. So this is sources of entangled photons, for example. And then we apply those to quantum sensing, which improves precision and resolution, that sort of thing, for example, for astronomical imaging. Okay, so let me start this talk by giving kind of a little bit of a recent history. In 2018, the National Quantum Initiative Act was signed into law that gives the US a plan for advancing quantum technology, and that in turn resulted in a tsunami of funding for quantum research and industry, which I'm sure you all have seen. And much of that is centered around so-called quantum 2.0 technology. So what is quantum 2.0? Well, first of all, quantum 1.0, that corresponds to the sorts of technology we're now really used to in our everyday lives. The semiconductor junctions and transistors in our computers, the lasers in our supermarkets. Quantum 2.0 uses the phenomena of superposition and entanglement. So that's what distinguishes it from the previous ones. So you might have had tunneling, you might have had quantization in quantum 1.0, but now we get to the really kind of quintessential phenomena that distinguish quantum mechanics from classical mechanics, and that's entanglement. So with that, you can build quantum computers that can break encryption, that can perform calculations that would be impossible for regular computers, and simulate quantum systems. You can also build new types of quantum sensors that allow better GPS, more mobile GPS systems, improve the sensitivity of probes in medicine, transportation, and fundamental science. And then you can build quantum networks. So these connect quantum computers in a new type of quantum internet. It allows you to communicate securely, and can be also used for distributed quantum sensing, like improving astronomical observations. You might have seen in the news the image of the black hole that was created by combining data from telescopes around the world. If you want to do that at optical wavelengths, you have to overcome loss of optical photons that are transmitted between telescopes, and actually quantum networks can help with that. Right, and so given this push for quantum 2.0 technology, where do we stand today? This is showing the evolution of the cell phone. Quantum technology is somewhere over here. So we're still building kind of the principal primary foundation for applications. However, out of all of the applications, turns out quantum networks are the closest and most accessible quantum 2.0 technology to actually making an impact on our everyday lives. So if we just look through like these different aspects, quantum cloud computing, you can access quantum computers online. There are over a dozen companies. Of course, these quantum computers have limited numbers of qubits that still cannot be used for the sorts of applications that I talked about for large-scale simulation, for example. Entanglement-based sensors still remain a research topic, and quantum networks, there are a few in the world. Even though they are out there, they're doing secure communication, these quantum networks haven't been publicly accessible. And so that's really where the thought came. What if we made a publicly accessible quantum network? And going back to that cell phone analogy, that would enable us to introduce this technology early on to more people, hopefully have their input, and just like the cell phone suddenly, exponentially expanded in its possible applications when more and more people could access it and could code and could think of new ways to use it. That's kind of the inspiration for making quantum networks public. All right, so why is it that quantum networks are somehow more accessible today than these other types of systems? Let's dive right into that. Right, so quantum. When we talk about quantum, sometimes we think of atoms, especially when we're talking about quantum computers, we're thinking about ions. These are not very accessible to us in everyday life. Things are not isolated in vacuum. But light is different. So if I were to turn off all the lights in the room and light a candle, we'd all see the light coming from the candle. And if I snuffed it out, eventually it would get dimmer and dimmer until just the wick was glowing. And at some point, it would just be a few photons arriving at your eye at a time. And it turns out that the human eye is extremely sensitive to light. So you are a single photon detector. The human eye can see as few as 1 to 3 photons. And so quantum science describes how photons and other quantum particles behave. So we have access to actually seeing that behavior for ourselves. So that's the first way in which quantum networks based on light are more accessible. Okay, so what are these quantum properties? First of all, there's superposition. If you want to go ahead and put on your 3D glasses, I'm going to give you kind of a way to experience superposition. So as you all know, light is an electromagnetic wave, and unfortunately I don't know if we can turn down the lights in the room. Thank you. And so I've indicated the oscillation of the electric field here with the up-down arrow and the wiggly line. And so you could have light that's vertically polarized. You could also have light that's horizontally polarized. And you can also have the photons in the superposition of the two. So with one eye, you can see that the light is a certain polarization with the other. And if you keep both your eyes open, you see both at the same time. It's not until you make a measurement, you make a choice of closing one eye or the other, that it becomes one of those polarizations. Okay, so that's the first quantum property that quantum 2.0 technology uses. I'll just mention that, the 3D glasses are kind of an analogy, right? But you can see superposition for yourself even if you just have some polarizing sunglasses. And so to show that, I have some polarizers in my pocket here. Okay, so because the screen is not polarized, I'm going to use this. Well, that's pretty. And then just show you that with polarizing sunglasses, you can block polarized light. Okay, so if you have these at home, you can do this. What's great about your computer screens is they tend to be polarized, so you can do this just with your computer screen without having this. And then what I can show you is that when I rotate to 45 degrees, I don't know if you can see that clearly. And if I were to put another polarizer that technically should block the light. So let me try to get this right here. Right. So you can see that it should block all the light because it's crossed with the first polarizer. But because I have my glasses in between at 45 degrees, some light gets through. Does everyone see that? That's a direct demonstration of superposition. If you understand the light as photons, as discrete particles, then after the first polarizer, they should be a certain polarization. And they should be blocked by a crossed polarizer. But by inserting one at 45 degrees, I've changed them to be in a superposition of vertical and horizontal polarization, so that when I apply the second polarizer, some of them get through. So if you think that to its inevitable conclusion, you've just witnessed with your eyes superposition. Okay. Of course, it all relies on you believing that light is made of quantum particles. Okay, so this is great. You can do this with IMAX glasses as well if you don't have polarizing sunglasses. I won't belabor this point. I think you all understand what I'm getting at. Right, so we write superposition in terms of these kets, which I like to think of as the P for possibility. So possibility, it could be oscillating up and down, it could be oscillating right and left. With superposition, already we have a problem. It starts to challenge some commonly held beliefs. Do objects have definite states before we measure them? Superposition implies that quantum particles may not, and this really raises the question whether there's an objective reality before measurement. This is exactly what Schrodinger dealt with Schrodinger's cat, if you want to enjoy that 3D image. Right, so he imagined, truly, if superposition is real, that means that we could put a cat in a box that's, whose life depends on the decay of a quantum particle, which is in a superposition of decaying or not decaying. Does that mean the cat is in a superposition of dead and alive? And these philosophical questions remain. It's not that we've solved them, or that this is just a cute little idea. This is a problem with our current understanding of quantum mechanics. All right, let's move on to entanglement. So entanglement takes two particles and puts them in a superposition such that when you measure one, the other becomes the same. So you can see that for yourself, measuring with your own eyes. When you measure, when you make a measurement, both of them end up being the same. Okay. And the way we would write that using our ket notation would be, particle one vertical, then the other particle is vertical, and vice versa. Okay, an analogy along with an undergraduate student in my group, we created this kind of tactile analogy for entanglement. If you take a piece of paper and you imagine particle one on this side and particle two on this side, and you write two possible states, let's say vertically and horizontally polarized. When you make a measurement, you fold the paper in half, and on the other side there's kind of blacked out regions. So you can't tell which state it is, and you make a measurement by poking a hole through one of the circles. You can see what will happen. A hole will end up going through both at the same time, and in that way, you'll always get the same state, okay? And so this is a representation that the particles are separate in space, and when you make a measurement, you impact both at the same time, instantaneously. All right, so I'd like to ask the question, why is this not entanglement? Can anyone say why that analogy isn't actually what's happening? Yeah.
Is it because when you fold the paper, you're bringing them closer together in space?
So, okay, so we're folding, we're bringing them closer together, okay. Any other ideas? I know I sprang this on you. You didn't expect me to actually stop and ask a question. I hate it when people do that. Let me say it another way. I have a 5-year-old. I read Dr. Seuss a lot. Consider socks in a box. There are two boxes of socks. The socks can be red or green. Which color they are is determined randomly by a machine, but the two boxes always have the same color socks. The socks are sent to distant locations like Timbuktu and Wananafi. The recipients open the boxes simultaneously. Great fox! They always find the same color socks in the box. What about this story? Can you find the problem? Why is this not entanglement?
They weren't in a superposition?
They weren't in a superposition. Very good. I like that you're wearing your glasses as you say that. Yes. Exactly. So with photons, we don't know what color the photons are. Not because it's hidden, but because the photons are in a superposition of colors. Their color won't be determined until the recipient sees the box, sees the color. At the instant that color is measured, the color of the other photon becomes the same. So the key difference is the colors are not predetermined, and that violates our concept that things have objective reality. And measuring the color of one instantaneously sets the color of the other. And that's that other belief system that is immediately challenged. Surely they have to be next to each other. And you mentioned, when you fold them, they are next to each other, right? And so that is one problem with the analogy. But the main problem is that the states are set ahead of time. Yeah. Even though in the folding paper analogy, You can't tell once you folded the paper which state you're going to poke a hole through. You could, in principle, figure it out. You could peek through. But with true entanglement, if you did that, you would cause a measurement, and that would result in loss of the entanglement. All right, so I've given a few analogies for quantum entanglement. As David Bohm said, every analogy is limited. Otherwise, it would be the real thing and not an analogy. So this is why we struggle. So what is the real quantum understanding for entanglement? Unlike most other science concepts, at its root, we do not know. We don't have an intuitive understanding of quantum phenomena. So this is leading us to quantum interpretations, which are useful to provide a sense of intuition. They are not yet proven. They are theories that provide a more first principles or foundational understanding of where entanglement can arise from. And the quantum analogies that I talked about can be linked to quantum interpretations. As a matter of fact, that paper analogy, it's directly related to this paper that was published just last year, talking about how wormholes can be used to explain entanglement. So basically, when you're folding that paper, you're generating an Einstein-Rosen bridge between the particles. Okay, and then when you make a measurement, they're immediately affected by that together. And so that's how weird it gets, folks. This is where we're at in terms of our understanding of this. If we want quantum technology to really impact the world and for people to use it, we need to show, the public and everyone that these are still open questions. Some things that we've discovered can be useful, and I think being more educated as a physicist even about really the limitations of our understanding and how amazing it truly is can be quite inspiring, I think, to anyone who learns about this, quantum technology. Okay, I'm looking at the time here. I don't want to, right. So, just check my, yeah. Right, so as I've mentioned, quantum mechanics challenges two commonly held beliefs, and this was really highlighted early on in 1935 by Einstein, Podolsky, and Rosen through their thought experiment, where they took two photons and said, well, if we separate them, just like we separate two socks in that analogy, we separate the two and we make a measurement, that means the other one somehow gets some information instantaneously that that one has been measured. That violates our concept of locality, or that things require speeds less than the speed of light. And so, yeah, we've got this issue of objective reality being challenged and also locality. And so, Einstein, attacked quantum theory. This was a New York Times article back in the 1930s. And so this idea that quantum theory was incomplete and maybe there were some hidden variables that could explain these non-local correlations, this remained in the air for scientists until the 1960s, when John Bell came up with a test for entanglement. And you can see on the board, he drew a diagram, and that's exactly what scientists later included as their diagram for their experiment, where they took entangled photons and performed the test that he suggested and showed that indeed photons can be entangled and have this non-local correlation. Then in 2022, some of those early scientists who did these experiments got the Nobel Prize. And what's great, and this goes back to the accessibility issue, is these experiments are relatively easy and inexpensive to set up, at least kind of at the first order kind of experiment. You can get more technical, as I'll discuss later. But they can be regularly incorporated in undergrad laboratories. So if you ever take Physics 403, which is a modern experimental physics class I co-teach, you can do a bunch of experiments using entangled photons, including a Bell test. Right, so as I mentioned, really sophisticated versions of Bell tests that make sure that there's no way the photons can somehow get information about what the state of the other photon is. Those have been done. Paul Kwiat has been an important contributor to that work. This was from 2015. They showed they could reject the hypothesis that local realism governs their experiment. Okay, so what can you do with it? What are these quantum technologies that arise from superposition and entanglement? Well, it's easy to see how communication could be affected. This was a nice little graphic created by one of the colleagues on that paper, Christopher Schaum. And he imagined two photons that are entangled. One is sent to Alice and the other to Bob, and they can be quite distant from each other. When Alice randomly chooses how to measure the polarization of a photon, so she might choose a basis of vertical and horizontal polarization, or diagonal and anti-diagonal polarization. And Bob also randomly chooses a way to measure the polarization of his photon. The cases where they chose the same measurement basis always end up giving the same result, which is in red. And those bits were generated randomly by whatever process results in a measurement result, which again, we don't know what that process is, but we can use it. So we can use this random number to encode information that we want to be secure. And what's great is if there's an eavesdropper present along the line, if they also try to get that information, they will make a measurement, which will cause the photons to collapse to a particular state, but they won't know what basis was chosen by Alice and Bob. And so when they try to make a copy of that photon that they measured and send it along, they might choose the wrong polarization. And that would show up as an error in the bits that they receive. Okay, now you imagine scaling that up. You can imagine sharing entanglement between quantum computers, different nodes of a quantum computer. You can do quantum communication. As I mentioned, you could use it for helping to sense astronomical objects. And this is the kicker, is unforeseen applications. You know, we have a handful of really cool ones that are driving all of this research, but there's surely more to be discovered. So the more people thinking about this, the better. Right, so let me get to the main idea here, which is let's go ahead and make this quantum network fully accessible. Start to talk about these ideas, which are very weird and mind-bending, and perhaps even a little bit relieving for some people, because maybe they thought science is over, you know, everything's been figured out, it's all just deterministically coded in a big machine. When the fact of the matter is, we don't know still, and so there's a lot to be learned and understood. So the idea for the public quantum network is to allow that extensive public engagement with hands-on participation, even educational aspects to that, as well as the fundamental research, because actually building quantum networks is state-of-the-art research. It's not easy, and there's a lot to be learned. And then finally, industry partners, as more and more of this, drive for quantum technology increases, there are more and more startups, more and more large companies interested in learning and applying this quantum technology in their products. Right, so, ultimately, these are the sorts of applications you can imagine: secure communication, quantum teleportation, which allows you to share the state of a quantum system without actually sending that system itself. So if you want to share the state of a photon without actually sending the photon through a transmission line, you can do quantum teleportation. The quantum internet could link together quantum computers, and then this idea is to generate new applications from more and more people, more and more diverse people thinking about its possible uses. So that idea came up around spring 2022. And the first thing to do when you want to build a quantum network is figure out how you're going to get that fiber link that connects you from one point to another. And quantum networks can also work in free space. They can also work via satellite. For intermediate distances, like on the scales of a few kilometers, fiber links can be quite useful. They're already in the ground. We use them for our internet service. And so if you can use a few of those fibers, that would be great to connect one point to another and send entangled photons back and forth. We needed to figure out a way of interfacing with the public. How are they going to actually make measurements on this network? How is it going to be as intuitive as possible? And then we needed to prepare to actually show it to the public with a launch event. We had our launch event in fall 2023, and then we're continuing to do a lot of research, and the and in summer of this year, we finished the full automation of the network. So I'm just gonna kind of walk you through some of those elements. So every building has a network closet. I don't know if you've ever been in one. They look like this. They've got racks with lots of fibers hanging out of them. And these fibers are linking underground. They're going through tunnels underground, you know, these conduits. And basically these colored lines are showing all the places where the fiber goes. And this particular map is from the i3 broadband company, which you know, graciously lent us a few fibers for this public quantum network demonstration. And they gave us fiber that links us between Loomis and the Urbana Free Library. What's wonderful about this is this fiber was, the whole intention of installing this fiber was to bring broadband internet to underserved communities. And it was created by the 2009 American Recovery and Reinvestment Act. And so it really, the whole purpose of it was to bring new technology or better technology to those who tend to get it last. So they were very on board with this concept of starting to do this for quantum networks. The Urbana Free Library, also in the name, it's free. It's all about access. They provide internet service. They run STEM workshops for kids. So they were also very enthusiastic about being the first public quantum node. So yeah, so this is a kind of the Google map version of that. You can see where Loomis and Urbana Free Library are. They're only about, you know, a couple minutes away. But when we asked them to link us up, it ended up being a 24-kilometer round trip in the fiber. And that's because they got to bring the internet to various places, you know, along the way. It's not going to be a straight shot. They also, I don't know what the reasons are, they particularly chose this fiber. We're using dark fiber that's not being used for the internet, and so they had to find strands that were, you know, not being used. So a lot of loss, you know, over 90% loss because of all the splices that were probably happening along the way. And so you might think, well, that's not going to work. It also has about 1,500 counts per second dark counts, which is probably from classical light that's you know, somehow getting into the fiber. So that's from the classical signal, or it could be just in the network closet. Someone leaves the light on, and that light can actually, you know, penetrate through the fiber and get into the transmission. We also characterize the polarization stability. We're going to be sending polarization entangled photons. And so we looked at the rotation of polarization as a function of time. And you can see over many hours, we only got a few degrees of rotation. And that's actually great because it takes just a few minutes to take a measurement, to do a full bell test. And over that time scale, you have pretty stable polarization. Stable enough that it wouldn't keep you from getting a nice result. And so this was good news. And what we do then is we can then optimize, we can compensate for any polarization rotation at the beginning of the day.
What's the source? Is this a
Yeah.
attenuated LED?
Yeah, so this is looking, I think this is just classical light, but then we have a quantum source that I'm going to show you in just a second. Yeah. Right, so the vision was to have a polarization entangled photon pair source. One photon is sent through the fiber patch panel over to the Urbana Free Library into their network closet. It's shot out in free space through a half-wave plate and a polarizing beam splitter, and then sent back over to Loomis, where it's combined with the other photon that stayed behind, and they're both detected. We're looking at coincidences of detecting the two photons. And then we measure their time of arrival, and we can then characterize characterize the state before and after propagation, for example, using this setup. And then the key thing is that at the public station, they can rotate the wheel, which rotates the wave plate in the network closet. And so they have control over what polarization measurement they make on the photons. Right, so getting to the source, how do you generate entangled photons? So we use a process called spontaneous parametric down conversion. The idea is that we have a crystal here. This crystal has a second order nonlinear optical susceptibility, which just means that electromagnetic fields can interact to second order in the crystal, such that if you put a laser through the crystal, the photons of the laser can be downconverted, so they can be annihilated and create two lower energy photons. And if you pump the crystal in two directions, such that you get photons in this state, so two photons, 1H, 1B, two photons, 1H and 1B, you have a probability of getting that in both directions, and you rotate one, you can end up getting entangled state HV plus VH at the output. So that's slightly different than the one example I showed you where they're always the same polarization. Here they're always different polarizations. So yeah, so this is the way we generate polarization in entangled photons. And ultimately it relies on the fact that you don't know in which direction the photons were created. So you don't know whether they're going to be in this arm or in this, going this direction or in this direction and being changed. Okay, so that's how you end up getting this entangled state. If there are any questions, please let me know. Right, so using this source, we got about 50,000 counts per second just of each photon individually, and then coincidence counts of about 2,000 counts per second. When we send that through our optical fiber, where we lose a lot of the light, we end up with about 100 counts per second. We also have a heralding efficiency that could be improved. That just means that when you measure one, most of the time you actually don't measure the other. It has a very poor efficiency for measuring the two together, and that may be due to just technical issues with the polarizing beam splitter that we're addressing. But, okay, so how good of an entangled state can we create? This is related to what we call the fidelity. So the fidelity to the target state that we want to create, how close is it to this state, is pretty good. We're at around 93%, and it lasts for a really long time. It doesn't seem to drift over time. And that allows us to do Bell's theorem test for entanglement. So Bell's theorem gives an inequality that would hold if local realism were true, and I kind of showed you that people have shown that it can violate Bell's inequality. I just want to briefly, I'm not going to go into detail here, I just want to briefly show what that looks like. So when you have two photons, you can separate them. So this is the idea. You have a photon pair source, and you send one this direction and the other that direction. And you can change what the polarization angles are to measure the polarization state of the photon. And Bell's inequality, or technically what we're using is the CH-SH inequality, but it's very similar, uses 4 different measurement settings of those polarizers at points A and B. And it's basically asking how similar are the two photons' polarizations for this situation, and then slightly rotated and slightly rotated. And then the last question is asking how different are they from each other? And you can kind of follow a logic argument that says that if you were to sum these and subtract this last one, the value you should get should always be less than 2. So that's the crux of Bell's inequality. And then if you get a value greater than 2, that means that they are non-locally correlated. That means that they are not determined ahead of time, and so when the measurement is made, one instantaneously changes at the same time as the other. Right, so we went ahead and tested our CH-SH inequality, and we found we got values well above 2, and those also continued for a long time, over 20 hours. And so all of this was good news in terms of the source's ability to kind of allow us to make this quantum network link. We also plotted, when we sent them over the network loop, we looked at the CH-SH value as a function of the angles chosen in the measurement setting, and we have this behavior here. And our thought was, when we first introduced this to the public, a Bell test would be a nice thing to let them do. First of all, we can make it happen. We showed that we can actually build it and have them do that test. And then secondly, it got the Nobel Prize in 2022. It's already a little bit in the public sphere. On the other hand, it's really hard to explain. So it's not that we expect people to have gotten it all, right? We don't even attempt to explain the Bell test. We just encourage them to make a measurement, and we kind of describe what a measurement is, and we encourage them to explore. And in exploring, they will generate this curve, and see that the photons are entangled. As a next step, we want to make a protocol that is a little bit easier to understand, and that's based on that shared randomness that I showed between Alice and Bob, where they can share a random number. So that's actually happening next year. We're going to install that, and because that required 2 stations. With just 1 station, basically, this was kind of the most interesting thing we could do. That's why we chose to do the Bell test for our first demonstration. Okay, so public interface. That was a whole other thing, how do you make this so that people can actually interact with it? We built this measurement setup. The idea is we want them to choose bases to measure the photon in. So we have horizontal, vertical, diagonal, anti-diagonal, and they rotate the wheel, and as they rotate the wheel, the lights change. And so when they choose to measure, in the HV basis, they'll find that these will be at maximum and minimum, and these will be even. They'll be even in their intensity. And that immediately, says, oh, by making a measurement in this basis, I lose information about what state they are in the other basis. Again, we didn't attempt to get them there, but eventually we hope we will. And that will be through making it more interactive, making it 2-person. We're also making a GUI that actually has a little character that says, no, now we're gonna do that, and tries to step people through it a little bit more. But anyway, so we designed this as our kind of baseline interaction with the network. So that's where kind of the rubber meets the road. That's where they actually get to make changes. And yeah, this is what the installation looks like at the Urbana Free Library. Feel free to visit. If it's broken, let us know. That happens a lot. We have here a description of superposition using the polarizers on a light screen. We have a really basic model of analogy of an entanglement source showing a laser going in and 2 photons that are entangled coming out, and then you rotate a polarizer in one, and that rotates the polarizer in the other. So it's like a non-hidden variable analogy. And then this is the measurement station where they can do the Bell test. So they can choose their angles based on the lights or based on a screen that shows kind of the polarization angles. And they submit that, and that does the Bell test. Okay, yeah, like I said, we provide only very limited instructions. We don't expect people to sit there and read a very long time. So until we have this kind of more interactive GUI going, that's what we decided to do. And our version 1 was all aided by people. So, we didn't have automation at the time. So we had someone there to move the wave plate based on the measurements that the person at the station decided to do that were communicated to that person. And then back over here, we had someone in the lab to make sure that the half wave plate was rotated to the angle chosen by the person at the public station. So this was all kind of with assistance, and that's how we were able to demonstrate the first Bell test in a public library. So we were ready. Last year we sent out this advertisement. We made a haiku where everyone can play with quantum particles. Come explore with us. That became our tagline for the public quantum network. And we got a great response. Definitely over 200 people. There were 700 clicks on the entrance detectors, so we lost count. We don't know. It was standing room only. Paul Kwiat and I gave a brief presentation. We did a live Bell test using the setup I just showed. And fortunately, we got a violation live. And we were visited by some wonderful community members, the youngest person to make a measurement on the public quantum network. Yeah, and we also gave out coloring books. This is available online. It's a great relaxing thing to do and also learn a little bit about quantum networks, so I encourage you to download it. Yeah, I just want to mention that, you know, this whole idea of a public quantum network, it really kind of builds on the already very strong public outreach around quantum principles that is done by Paul Kwiat. If you've never done the lab escape that he runs, it's a lot of fun, especially the latest versions. They have a lot about quantum networks in them and quantum technology. And then Smitha Vishweshvara has this amazing art science celebration, and through her, I've been able to, you know, connect with dancers and think about how to express these concepts in a way that might be more accessible. Again, accessibility to people who think more physically, you know, and that's not so hooey stuff because if you look at the early, you know, the early scientists, some of the great scientists such as Einstein, Bohm, they all talked about the physical sensations that they felt when they were coming up with these amazing theories and ways of describing how the world works. So it's not out of the realm of possibility that by incorporating more of that, it actually might make things a little bit more intuitive and perhaps link us to, you know, abilities that we kind of not really taken advantage of. So I'm really excited to see where that goes. Okay, so where are we? We have over 400 now, over 400 interactions with the setup since November. As I said, we know its deficiencies. At least we think we do. There's probably more that we don't know. But so we didn't expect this to make a huge impact in terms of people's knowledge and understanding, but it's our first attempt at building that bridge. It's required us to make these components, to make the quantum network itself, to make components that kind of start to feel intuitive again, start to think about how we describe things and make analogies. You know, this paper analogy that came out of our thinking just a few months ago in the summer, where I was like, we need to have more of things like that. So that paper analogy, and all of these are building kind of, like I say, bridges to the public. What's amazing is that as we're doing that, we really see the lack of, the deficiencies in the formal education around physics. Because people simply aren't exposed to these ideas until, they take quantum mechanics, and even then, it's at the back of the book. Or it's very technical, like, oh yeah, qubit, here's how you manipulate a qubit, but the philosophical implications are kind of always shoved under the rug. And yet, when you go to explain this to your friends and the public, that's the first question they're going to ask. How does it work? And if all you say is, yeah, we don't know, but there are certain theories out there, and I would encourage, students to spend some time on their own if they don't get this in their classes, just studying what those are and starting to think through. It's amazing how much insight you get into your own experiment, and perhaps more depth, perhaps more appreciation of what you do in the lab when you kind of have a more broad philosophical understanding of where it stands in the big picture. So yeah, it's been beneficial for my research as well, my research group. Well, we finally did get it automated, and so that's what's shown here. The people are replaced with connections to a VPN, and we've got Raspberry Pis connected over, network with TCP protocols and stuff that I don't, this is not what I do. Fortunately, I have amazing students like Benjamin. And fortunately, we've also gotten some collaboration with people from NCSA to help us make software that's really robust and allows us to scale this to more and more nodes. Right, so here's just a brief picture of that. At the Urbana Free Library, we have a Raspberry Pi that runs this interface on the computer. It sends the measurement requests made by the user and gets and displays the result. Those measurement requests go over to the network closet, where it rotates the half-wave plate in the path of the photons, and it also goes over to the half-wave plate in the lab that rotates the set of photons that kept in the lab. And then, that in the lab, we have a software that runs the automated measurements once those settings are made, and then sends the result back to the library. Yeah, so with that full automation, we could take, measurements over a long duration and again confirm that it all is pretty stable. We think that this is when someone went into the network closet and shut the door too hard or something like this. So stuff does happen. Yeah, so what's next? Well, the next node is going to be at Fermilab Visitor Center, the Laterman Science Center. And it's going to be similar to what we're going to install in February at the Urbana Free Library, where there are going to be 2 people. So 2 stations, they can do secret message sharing, and that's a lot easier to explain than the Bell test. They'll still be able to do a Bell test if they want to dive into that, and I imagine we'll get better and better and better at explaining that in an accessible way as we continue. We're also doing a lot of work in education, so I'm partnering, not with TeachQuant, it turns out, but with IPASS, which is a great physics program for high school teachers to improve their physics curriculum. And I'm going to introduce quantum concepts to the teachers and have them incorporate that in their classrooms and potentially link that to kind of field trips and that use quantum network nodes. So yeah, a lot of people have contributed to this work. I don't think everyone's even on here, but certainly some of the key people. As I mentioned, Paul Kwiat is a great collaborator on this. We wouldn't have been able to do it without the amazing, participation of that fiber network, and then the Urbana Free Library, as well as for the launch event that raised a whole other question of how to make it engaging, and that thanks to all of the media relations people at UIUC for their help with that. Yeah, and I think that brings me to the end, so I hope I leave you in an optimal superposition of awake, and we'll call it asleep for the sake of that kitten. So thank you very much for your attention.